Hey everyone, let's just admit it. Electromagnetic theory is absolutely notorious for being one of the most brutal courses in any engineering curriculum. But, it really doesn't have to be. Today, we're going to decode the complex math behind electric dipoles and flux lines, and we're going to use real-world analogies so these concepts actually stick in your brain permanently. If you've ever stared at a page of vector calculus and just thought, okay, what does this actually look like in the physical world? Well, you're in the exact right place. Let's get into it. Okay, let's dive into this. Here's our roadmap for today's explainer. We'll start with the dipole dilemma, move on to visualizing the electric dipole, cover the dipole formulas and math rules, do a real-world dipole walkthrough, look at the high-order multiple gotcha, and finish up with key takeaways and a final review.
All right, section 1, the dipole dilemma. So, here is a massive pain point for engineering students dealing with electromagnetism. You already know Coulomb's law for a single-point charge, right? That's basic. But why does the math suddenly morph into a completely different set of formulas when two opposite charges get really close together? Well, by the end of this explainer, I promise you're going to perfectly understand how to solve problems involving closely spaced charges without getting completely lost in the formulas. Let's establish our absolute baseline from the text. What actually is an electric dipole? Simply put, it's formed when two-point charges of equal magnitude but opposite sign, so a positive q and a negative q, are separated by a small distance, which we'll just call d. That's it. That's the textbook definition. But to really grasp what this does to the space around it, we've got to visualize it.
Which brings us to section 2, visualizing the electric dipole.
We're going to anchor this abstract definition into a concrete visual analogy, so you literally never forget it. Take a look at this physical setup of a dipole along the z-axis. We've got our positive charge plus q sitting at the top, and our negative charge minus q down at the bottom. They're separated by that small distance d. Now, out there in space is our observation point p. To figure out the potential at p, we draw two distance vectors. Vector r1 connects the positive charge to p, and vector r2 connects the negative charge to p. And then there's vector r going straight from the origin to point p. It kind of looks like a messy triangle right now, but just keep this exact physical geometry in your head as we look at how the fields actually behave.
And this brilliantly illustrates the difference in the resulting fields. On the left, we're looking at a single-point charge. Think of this like a water balloon bursting. The force just pushes radially outward in perfectly straight lines, right? In all directions. But look on the right. That's our dipole. It's no longer just pushing. It's a push-pull system. It's exactly like a circulating water pump. The electric flux lines are forced out of the positive charge, and they loop right back around to get sucked directly into the negative charge. It creates this beautifully continuous looping flow of energy. Now, pay close attention to those dashed lines. Those represent equipotential surfaces. Think of an equipotential surface kind of like a flat contour line on a hiking map. If you're walking along a perfectly flat mountain trail, you're not doing any work against gravity, right? In the exact same way, if you move a charge along one of these dashed equipotential lines, absolutely no electrical work is done. Zero. And here is the absolutely crucial visual rule you've got to remember. Those solid electric flux lines are always perpendicular or normal to these dashed equipotential surfaces. Moving on to section 3, dipole formulas and math rules. Okay, so now that we have that circulating water pump analogy in our heads, let's systematically break down how the textbook derives the math. The text starts with the general potential equation, equation 4.77, which really just adds the potential of the positive charge to the potential of the negative charge. Simple enough, but dealing with those individual R1 and R2 distance vectors gets incredibly tedious. So we apply a massive mathematical shortcut, a distance assumption. And this simplifies that giant, ugly equation down to the elegant dipole potential formula, equation 4.80. So, what is that magical assumption? It's this exact condition right here. If R is much greater than D, this simply means our observation point P is very, very far away compared to that tiny little separation distance between the two charges. When you step way back like that, those R1 and R2 vectors essentially become parallel. This mathematical condition is the absolutely crucial assumption that allows all that complex geometry we saw earlier to just collapse into a clean, solvable formula. And that clean formula relies entirely on a new variable called the dipole moment, represented by a lowercase p. The dipole moment p physically represents the charge magnitude, q, multiplied by the distance d. Crucially, though, this is a vector, and it is always directed from the negative charge to the positive charge. Once we define P, our general potential, V, simplifies beautifully to the dot product of the dipole moment and the directional unit vector, all divided by 4 pi epsilon 0 r squared. Let's see this in action in Section 4, Real-World Dipole Walkthrough.
Let's actually bring this math into reality because field mapping has some incredibly cool real-world applications. The text points out that the human heart beats in response to an electric potential difference and literally acts as a dipole. Mapping this out helps detect abnormal heart positions. So, keeping that biological pump analogy in mind, let's solve a practical problem right out of the text. We need to find the potential at the origin from 2 different dipoles. Dipole 1 is sitting at z equals -2 with a dipole moment of -5 AZ nanocoulomb meters. Dipole 2 is at z equals 3 with a moment of 9 AZ nanocoulomb meters.
All right, here's the step-by-step logic. First, we identify our observation point R, which is the origin, 0, 0, 0. Because our source points R prime are sitting out at z equals -2 and z equals 3, we can't use the basic formula. We must use equation 4.81. We map the distance vector from dipole 1 to the origin and calculate that potential. Then we do the exact same vector mapping from dipole 2 to the origin. Finally, using the principle of superposition, we just sum up the potential from dipole 1 and dipole 2. If you follow those steps and map out the vectors carefully without skipping any mental steps, you literally cannot fail this problem.
Next up, Section 5, the high-order multipole gotcha.
Now, what's really interesting about this slide is that it highlights a classic trap that trips up engineering students all the time. You absolutely must pay attention to how fast these fields drop off or decay over distance. Think of it like a fading echo. For a single point charge, our monopole, the potential drops off as 1 over r, and the electric field drops off as 1 over r squared. But consider our dipole. Because that positive push and negative pulls start to actively cancel each other out the further away you get, its echo fades much faster. A dipole's potential drops as 1 over r squared, and its E field dies out extremely fast, varying inversely as r cubed. Whatever you do, do not use point charge drop-off rules for a dipole problem.
And, it just builds from there. If you take 2 dipoles and put them together, you get a quadrupole. The E field for a quadrupole decays even faster, dropping off as 1 over r to the 4th. Take 2 quadrupoles, now you have an octupole, and that drops off at 1 over r to the 5th. The rule of thumb here is as you add more complex arrangements of charges, the fields decay at increasingly rapid rates. All right, let's wrap this up in Section 6, key takeaways and final review.
We have covered a lot of ground today, so let's cement this into your long-term memory with 3 rapid-fire takeaways. Number 1, the dipole moment P is charge times distance, and remember, that vector always points from the negative charge up to the positive charge. Number 2, our big exam gotcha. A dipole's electric field drops off drastically faster than a point charge's, varying inversely as r cubed. And number 3, electric flux lines represent that push-pull flow, and they are always perfectly normal or perpendicular to the equipotential surfaces where zero work is done. If this explainer helped decode the math for you, definitely make sure to hit that subscribe button. We're constantly rolling out more electromagnetic compatibility survival guides and rigorous engineering tutorials to help you master these concepts. Before we go, I want to leave you with one final kind of provocative engineering thought. The text mentioned that the human heart can be mapped as an electric dipole. So knowing what we just learned about that rapid 1 over r cubed drop-off rate, how do you think engineers have to design the sensitivity of next-generation microwave medical imaging sensors just to detect those signals from the heart all the way at the surface of the skin? Really think about the engineering challenges of that fading electrical echo. Thanks so much for joining us for this explainer, and keep building.